Okay, hi everyone. So welcome to Math 030 Multivariable Calculus. And for this video, I will discuss more into the introductory topics in vectors and the geometry of space. So for this succeeding subtopics, we have the following intended learning outcomes. So we want to illustrate the 3D coordinate space, solve for distance between 2 points in 3 dimensions, perform vector operations and interpret their results, write a vector as a linear combination of standard unit vectors, analyze vectors in a space, solve for angle between two vectors using the dot product, evaluate the cross product of two vectors in a space. Okay, so we have the following outline. So we have three-dimensional coordinates, the vectors, the dot product, the cross product, equations of lines and planes, cylinders and quadratic surfaces. So for this tool, now we have the applications of vectors in the geometry of space. We will not get into deeper details with this tool, but I will give you an idea on how to solve for these two topics. No? Okay, so let's start with the three-dimensional coordinate space. So basically, the three-dimensional coordinate space has three axes. No? So we have the x, y, and z coordinates to represent the space. So any point in space, let's say inside a room, no, any point at any point here could be represented by this x, y, and z coordinates. So we have these three planes now that we call which are the xy plane. So basically, the xy plane is the combination of the x and y coordinates. No? So everything that is x and y will represent this floor, no, or this plane. And then for the right wall, we have the yz, and the left wall with the xz plane. Okay, so what is the comparison, or how do we transcend, no, from the plane to the space? So in the calculus, and in linear algebra, we discuss planes and ordered pairs, uh, and a lot of things, no? But we will now discuss about ordered triples. So instead of just x and y, we have another variable, which is z. Or sorry, not another variable, but another coordinate, which is z. So instead of x and y, a and b, we have a, b, and c to represent our point in the space, instead of the plane. So the formal representation of the two-dimensional point, okay, is this r squared. So meaning, what does this mean? We have two ordered pairs to represent this plane in the space using real numbers. So we only utilize the real number set. And then for three-dimensional, or the space, we have this r cube. So r cube, again, we have three ordered pairs with a constraint of only dealing with real numbers. So we do not have the complex numbers. Okay, so let's have an example on how to plot the given points in a space. So we have the 2 points, we have -4, 3, and -5. So what does this basically mean? We have this x, we have this y, and this z coordinate to represent our point. So to visualize that, we have this graph to represent this point. Okay, so how do we get there? We start with the x, no? So with the x, we have this x axis, no? Okay, so this will be different, or this will be a different orientation from what we are used to in the other mathematics previous to this. So the x here, the positive x here is through the screen, and then the negative x-axis will be into the screen, no? If you could imagine, no? So into you, no? Sorry, into you, and then into the screen. So positive into you, negative into the screen. Okay, so -4 is this, and then after that we have the y. So y is this. So y positive is to the right, y negative is to the left. So that is intuitive, no? Okay, so we have 3 here, so we have to count 3, 1, 2, and 3, for example. So this will be your point. And then after that, the z coordinate will be the -5. So the z axis will be representing this, this translation. So the positive z will be upwards, the negative z will be downward. So it is intuitive, no, in some sense. The z and y, only the x will be something new. So negative 5 here will be downwards. So the final point or the terminal point will be also the point that we are interested in. So therefore, for this other point, we represent this. So we have positive 3, we have negative 2 to the left, and the negative 6 down. Alright, it is that simple now to have a point in a space. Now, what if we want to plot this x is equal to 2 in our cube? So what does this mean anyways? No? So when we say x is equal to 2, we have a vertical line, no? If you could remember in your analytic geometry or your pre-calculus classes or in your calculus classes in general. But we are used to plotting x is equal to 2 in R2, meaning in just 2D space. Now we have just the x and the y. But how do we show this in 3 dimensions, no? So in 2 dimensions, we have this vertical line to represent x squared. In R2, no, we have this space. We have only x and y. But if we include z, we can see that our line will become a plane. And also it will become a fabric, no, or a mesh or a membrane, okay, that is extending infinity on all sides. Okay, actually this all extends to infinity through all sides. Okay, so there is a difference in plotting lines in a plane versus in a space. So in a space, your line will become a plane. Okay, so you can imagine here, this is x is equal to 2, right? So this is positive. So therefore, this will be your representation. If this is just a space, sorry, not here, but in here, this will only be a line in, if this is only considered, no, it is x and y. But again, in space, it will also extend in both ways. No? So we have this upper and then this lower. Okay, so let's move on to the next slide. Okay, so we have a way to also figure out how to find the distance between 2 points in 3 dimensions. So if you could remember, if you have to find the distance between 2 points in 2 dimensions, we have the Pythagorean theorem, no? We just erase this one. Okay, but in 3 dimensions, we add another term, which is also similar, no, to our formulation. Okay, so we have the z-coordinate, the difference in z-coordinate squared. So this is similar to the Pythagorean theorem, no? And actually, this came from the Pythagorean theorem. So I won't show you anyway how did we get here, but you can try this, no, at home. You can derive for this formula. Okay, so the distance between 2 points is represented by this 2 vertical bars or 2 vertical lines, no? Which usually means absolute value sometimes, or it could mean the magnitude or the length, or sometimes we have 2 vertical bars, which means the norm, and sometimes it also says, in some contexts, it also means the distance, or the length. Okay, so given we have 2 points, we could find the distance. Okay, so how do we solve the distance from 2 points? Let's say we have this given point P, we have given point Q. Okay, so how do we find this one? So again, to find the distance between PQ, we have this formal notation to represent this, and this is equal to the square root of the difference of their squares, or the squares of their differences for each of the coordinate. So we want to find the difference between these two, so we have 2 minus 1, and then squared, and then we have negative 3 and negative 1. So we have negative 3 minus negative 1, okay? So be careful with the negative sign. And then plus, we have 5. Actually, we mashed this up a bit, no? So this should be 1 minus 2. 1 minus 2, sorry. And then we have 5 minus 7. But anyways, guys, even if this 2 are swapped, it will still have the same answer. And so to simplify this, we have square root of, so this will become negative 1 squared, so 1. This will be negative 3 plus 1, so negative 2. So negative 2 squared is 4. And then we have here negative 2 squared is 4. So we have here square root of 9, no? So 1 plus 4 plus 4 is square root of is 9. So the square root of 9, that is equal to 3. Therefore, the distance between these 2 points is equal to 3. Or to be exact, 3 units, no? Okay. So now, how do we find the equation of a sphere, no? Knowing that we have the distance. No? So actually, as the sphere is a representation or a locus of points at which the center is equidistant, no, to this point in a constant manner. So imagine you have a point which is the center, and this point is equidistant, no, in any what do you call this, at any perspective at a constant rate, no. So we have this constants, no, constant value, which is the radius, constant. So we could form here a sphere, or you can start with a circle, and then a sphere in 3 dimensions. Okay, so how do we solve for this? Or how do we represent this equation of a sphere? We have this graphical representation, and we have this standard equation of a sphere, wherein your center is h, k, and l, meaning that is the x, the y, and the z coordinate respectively of your center, C, and it is equidistant to a point or a locus of point P using the constant distance R. Okay? So, moving on and trying to solve a given problem involving spheres, since it is equidistant with this center point, we want to find the equation of the sphere with the center at 3, -1, and 6. It passes through the point 5, 2, 3. So we have a given center that is 3, -1, and 6, and then we have a given point. If you would recall, we have the equation of a sphere, which is x minus h squared plus y minus k squared plus z minus l squared is equal to r squared. So the x are given, no? So this is actually your x, y, and z. Okay, so x, y, and z are given. The center is given. So center, we have HKL. So the center is given, HKL. We do not know, the only thing that we do not know yet is the radius. So we want to solve for the radius first. And how do we solve for the radius? We have this equidistant point, or the point, the locus of points P is equidistant to the center C. So the point P and the C, okay, is the radius. So to find this radius, we have the difference between these two, which are, actually we could solve this already, no? So if we substitute the value here, we could get the R. No, sorry about that. We could actually get the R here. So the R here is equal to, we have x minus h squared plus we have y minus k squared plus a z minus l squared. And then we can substitute the value to find R. And then later on, substitute the value R to this equation. So to solve for this, again, we have x minus h. So we have 5, no? So this is x, y, and z. So we have 5 minus 3 squared plus we have 2 minus -1 squared, and then we have 3 minus L. So L here is 6 squared. Okay, so to simplify this, we have R that is equal to, so square root of, so this is 2, 5 minus 3 is 2, so 2 squared is 4. And then we have 2 minus -1, so this will become 2 plus 1, so 3. So 3 squared is 9. We have 3 minus 6, so -3. -3 squared is 9. So the answer here will be, so we have 4 plus 9, that is 13, plus 9, we have 22. So the answer should be square root of 22 for the radius. No? So no need to solve for the numerical value of this. We can substitute this back to our standard equation. Therefore, the equation of the sphere is when we substitute this h, k, and l, and then this r. So therefore, the final answer will be x minus h, so 3 squared plus y, so y minus -1. So we could just omit this negative sign, no? So this will just cancel out. Therefore this will be y plus 1 squared, and then we have plus z minus 6 squared is equal to r squared, wherein r is equal to the square root of 22. So the square root of 22 will become just 22. So this will be your standard equation of the sphere. Okay. So let's move on to the next one. Okay, so let's discuss about the vectors. So what are vectors? Vectors are represented by an arrow or a directed line segment, which basically mean we have a length, no, of this arrow and this direction of this arrow. So basically, and we denote these vectors using a boldface V, so meaning naka-bold, no, yung kanyang font. Or sometimes it is hard to write this in the board, so therefore we have to, we can use an alternative notation using this arrowhead in its head, no, arrowhead in the head. Okay, so let's move on and let's discuss an example of a vector visually. So the vector V, no, so we notate this directed line segment as V, no, a boldface V, which has these 2 points, A and B. So A is the tail, no, it came from the tail, no, or the initial point, and we have the terminal point B, which is also called the tip. Okay, so we notate this. We have the initial point, the final point, the tail, or the tip. Now, if let's say we have two vectors u and v, and if they have the same length or magnitude, in other words, and also in the same direction, therefore they are called equivalent vectors. And another thing to take note, if a vector has no magnitude or no length, then it is called a zero vector. Okay, so how do we add vectors? Now, let's say you have two vectors. Usually in the context of physics, now we have two forces. If we add two forces, what happens? It will become a resultant, or there will be a resultant vector or a resultant force representing their sum. So let's say we have a vector u, we have a vector v. A visual representation or a graphical representation of that will be this connecting point of u plus v. So we have the initial point of u, or the tail of u, and the tip of v. So we connect this u and v using the tip of u, no? So yung dulo ng u, and then yung initial point ng v, no? To represent this vector. So again, no, we have this u, and then we have this v. So this should be in boldface, no? Which is denoted as u plus v. And then again, the addition, no, we have this u, and then we add this v, and then the sum of this u and v is this connecting line of u and v. Now we call this a triangle law because it makes a triangle, no? And alternatively, actually you can do the other way around. You can start with v, okay, pwedeng yung v muna, and then add the u after that using the tip of v, and then attach the tail of u, so that the endpoint here will be this. Ayan. Okay. So this is called the parallelogram law because it looks like a parallelogram, you know. Okay, now again, no, recalling this concept, if instead of u and v we have vectors a and b, how do we draw the sum of a and b? So again, no, if we remember, we have a vector, which is this, and to add these two vectors, we just connect them, no, together. So we have vector a, and then connect the vector b. Therefore, the sum of this vector a and b will be this initial point and this terminal point, no, through the triangle law. Or, no, in other words, we could start with b. We could start with b instead of a, and then add the a vector, and it will be the same sum a plus b, which is the parallelogram law. Okay, so moving on, in regards not to, consecutively with vector addition, hindi lang tayo pwede mag-add, no? We could also perform the scalar multiplication, no? So how do we multiply a vector with some scalar value? When we say scalar value, it is just a single number, no? Just one number, a single number. So if let's say we have vector b, the visual representation of the scalar multiplication of b with, let's say, 2, so we have 2 times b, it will double in length, no? So if this is the initial vector, it will double in length, okay? And if, let's say, we multiply this by a fraction, no, which is 1/2, then it will be scaled accordingly. So we have this original vector v. If we multiply this by 1/2, then it will be half. If we multiply this by a negative number, no, let's say -1, the direction will be swapped. Okay, so instead of the direction here going upwards, it will be in the opposite direction if we multiply this by a negative number. And similarly, if we multiply this by another number other than -1, it will change in direction, no, in the opposite direction, and it will be scaled accordingly. So magmumultiply tayo ng 1.5, so it will be larger, no, by a half our vector length. Okay, so now do we find the vector difference of u and v? So the visual representation of adding this, or finding the difference between two vectors is similar to what we did last time, but instead of adding the tip, no, and connecting the two vectors, we have to find first the inverse, no, not the inverse, but the opposite direction of your vector. So if you have u and you have v, and you want to find u minus v, so v will become the negative vector, so therefore the direction of v should be swapped accordingly. So this will be your new vector, and then perform the connecting, no? So if you have, let's say, you start here, u, and then you add this negative v, so effectively you're adding this negative v, and then this will be your connecting line for your difference, no, or your sum, no? Essentially, this is the sum of u plus negative v. Okay? So you can do this alternatively. You can start with negative v, and then add the u, you will get the same value. Okay? So, again, no, this is the parallelogram law. Now, let's discuss the components of a vector. So, what are the components of the vector? So, in a vector in a plane, we have essentially two coordinates, which are also the components of our vector. And these two coordinates will represent this terminal point in our vector in a plane or vector in a space. So, again, we have two coordinates in the plane, 3 coordinates in space. Okay? So our component here, we have A1. This will be your A1, this length here. If you visualize this, and your A2 will be this vertical. No? Sorry, this will be your vertical. And then for your A here in the space, so we have here, where is A? So A here is, A1 here is this. Okay, and then A2 is this. And then A3 will be this connecting line. Okay. So this, again, we have 2 components for space, for plane, 3 components for space. Okay, so find the vector given, or finding the vector given the initial and terminal points. So let's say we have a given 2 vectors A and B. What is vector AB? So how do we do that? No? So if we have a given initial point, we have a terminal point, okay, we can find a vector AB. So how do we do that? We just subtract their coordinates, essentially. So let's say you have a given point A and B. To find the vector that represents their initial and terminal points, we just subtract their coordinates. No? So for x, find the difference of x, find the difference in y, find the difference in z. So let's have an example doing just this. So if this is our initial point and this is our terminal point, what is that vector representing this directed line segment. So we have a distance in between these two vectors, which is also the length, and then the directionality incorporated in between these 2 points. So again, the vector, no, vector AB. So since we are connecting these two vectors, sorry, these 2 points, A and B, associating it with the vector using this arrowhead. So this will be equal to, no, so we have this notation, we have this left angle, we have 2 minus -2, okay, for the x coordinate, we have -3 minus 1 for the y coordinate. Actually, it should be the opposite direction nga pala to, ano? It should be the terminal point first, no? I'm sorry, really. It should be -2 first, no? Before the +2. So this should be 1 minus -3. Ayan. And then for z, we have 1 minus 4. Okay, so this will be our vector. So therefore, this will be -4. We have 4, and then we have -3. It's that simple. Sorry, we have a solution pala dito. Sige. So is it the same? Okay, it is the same. So this will be your vector. Yeah, so we could represent this into this form using this notation, the left angle and the right angle. Okay, so now how do we find the length of a vector? And we denote this as in this form. We have two vertical pair or vertical bars. We have two vertical pairs of vertical bars. So given a vector A, we have these two components A1 and A2. We could find their length by finding the square root of their, or of the sum of their squares, or the sum of the component squares. Okay, so for 2 dimensions, we only have to square 2 terms, but for 3-dimensional vector, we have to square 3 terms. Okay, so for addition and subtraction of vectors, we have this. So we can add A and B by adding them entry-wise. So we have 8A1 plus B1. We have A2 plus B2. It's that simple. We already know this, no, in our linear algebra. And if we multiply a vector by a constant, no, or a scalar value, we just distribute the scalar value effectively through all the entries, no, or for all the components. Okay, so this will be the same for all, or for higher dimensions. So we just add them entry-wise. If it is a scalar multiplication, we just multiply the scalar value for each of the components. Okay, now so let's have this example problem. So given A vector and B vector, find A, or the length of A, and the vectors A minus B and 2A plus 5B. Okay, so how do we find the length A? So to find the length A, this will be equal to, again, the square root of the sum of the squares of their component. So we will just square this. Yeah. So the length A, that will be equal to the square root of 16 plus 9, which is equal to, so 16 plus 9 is 25. So therefore, the square root of 25 is equal to 5. So this will be your length. So 5 or 5 units. Okay, so to find A minus B, so to find A minus B, we have to only subtract the two vectors entry-wise. So A here is positive, so this will be 4, and then minus -2. So we have here 4 minus -2, and then for the other one, we have 0 minus 1, and then we have 3 minus 5. So the difference of these two vectors will be 6, no? So 4 plus 2, -1, and we have -2. Okay, and then for 2A plus 2B, okay, for 2A plus 2B, we have 2A plus 2B, sorry, 5B. That will be equal to 2 multiplied by A, 5 multiplied by B, and then we add this 2. Okay, sige, let's try doing this one by one. So you have 2 multiplied by the vector 4, 0, 3. plus we have 5 multiplied by negative 2, 1, and 5. Okay, and then simplify this. So distribute this 2, distribute this 5. We have 8, 0, and 6. And then plus we have negative 10, 5, and 25. Alright, and then simplify this. So we add them entry-wise. So this will be equal to negative 2. We have 5, and then 6 plus 25 is 31. Okay, so this will be your final answers. Alright. Okay, we have an answer as well here. Okay, sige. So this will be the same answer with what we got, right? Okay, so same lang naman. So moving on, we have the different properties of vectors. I will discuss this thoroughly. This is similar to what have been discussed in your linear algebra course, or in general, the properties of real numbers. So we have the commutative property of addition, the associative property of addition, the identity or the zero identity, and then the inverse identity or inverse addition property, Okay, and then distributive property of scalar, And then we have similar distributive property of scalars, pero yung E naman hindi distribute natin, or we distribute this E vector with our scalar values. And then this one, distributive, associative, and then this identity property, unit identity property. Okay, so let's talk about the standard basis vectors. So basically, in simple terms, we have a representation of I with regards to the direction of the x-axis, J with respect to the direction of the y-axis, and K with respect to the direction of the z-axis. So again, we have this as x, we have this as y, we have this as z. So formally, we call this the standard basis vectors. More into that later during the end of the portion or the middle part of the course. Okay, so given, let's say we have a vector A that is represented using the standard basis vectors, ijk, we could represent this in its component form, which is 1, 2, and negative 3. So essentially, it is the same thing, but in a different way of representing a vector. So these are, so don't be confused, these are the same, We just have the standard basis vector notation, or sometimes we call this the unit vector notation, and then we have this component vector notation. Okay, so let's discuss about the unit vectors. So basically, unit vectors are vectors with a length of 1. And let's say you have a given vector, you can find a unit vector associated in that direction using this formula. Okay, so what does that mean? Let's say you have a given vector A, just divide the vector A by its length. Okay, so divide it by its length, it will become the unit vector U. Okay, so let's have this, I think we have an example here. So let's say we have a given vector. Okay, so let's call this, for example, let's call this the A vector. So the A vector is equal to 2i hat. Actually, we have this hat. For the standard base vectors, we have minus j hat minus 2k. So don't worry about the notations, guys. You can just write ijk if you want. Alright, so how do we find the unit vector? So we have u that is equal to a vector over the length of the a vector. So we already know the a vector. We just do not know the length of the a vector. But we can solve this, because we already know how to solve for the length of the unit vector or the length of the a vector. So we have the vector a. Okay, so let's just write this down. Sorry, it should be k. And then for the length of your vector, we have the square root of the sum of the squares. So we have 2 squared plus negative 1 squared, and then plus negative 2 squared. Okay. So to simplify this, we have 4, we have 1, we have 4. So this will be 4 plus 1 plus 4, which is 9. So the square root of 9, and then we have again 2i hat minus j hat minus 2k hat. So to simplify this, we have this as 3. Therefore, we just distribute this effectively, no? Or basically, we're just multiplying 1/3 to our vector 2, -1, and -2 effectively. So therefore, the final answer for the u vector, actually, it should have an arrow now. So the u vector will be equal to make this the same notation, no? We have 2 over 3 I hat. We have negative 1/3. Sorry, it should be plus. Sorry. J hat, and then minus 2k hat. Okay, so this will be your unit vector associated in that direction. Sorry, over 3 pa pala. Ayan. Okay, or we have this notation. We have 2/3, negative 1/3, and negative 2/3. Okay, so this is also another answer. Okay, ayan. We have an answer as well here. Sorry, I didn't see that coming. So application of vectors. We have this given problem, and then how can we apply the concept of vectors in solving this problem? So a 100 kilogram weight hangs from 2 wires as shown in the figure. Find the tension, forces T1 and T2 in the wires, and the magnitude of these tensions. Okay, so we have this given diagram of a weight, no, that is pulling through these wires, no, which has a tension of T1 and T2, and we have a given angle of this tension, this wires with respect to the horizontal, which are 50 degrees and 32 degrees. So now how do we find the tension? So basically we want to find the T1 and the T2. If this is in boldface, we're trying to find for the vectors. Ano? Kapag naka-boldface. So we have this. We want to find the vectors. And then we have to find the magnitude or the length. Okay, so let's solve this one. So utilizing vectors and the rule in geometry, so since this is 50 degrees, therefore, if we extend the line here, this will also be 50 degrees, and we can find the component of our vectors. So we have T1 as our first vector. So we have a component in X of this T1. We have a component Y in this T1. And then for T2, that will yield the same thing. This angle is 32 degrees. So therefore, the angle here will also be 32 degrees. Therefore, their components, so the X here, and the Y here are the components of this T2. Okay, and then we have the weight, which is 100 kilograms. Alright, so now how do we find an equation, we have to find the vectors T1 and T2 and also their magnitudes, or in other words, the length of these vectors. So in physics, we have this principle that if this is in equilibrium, meaning it is not moving, it is at rest, it has no acceleration, the sum of the forces will be equal to 0. So that will yield the same principle in vectors if we have the addition of these three vectors, so the addition of T1, T2, and this vector W, okay, the sum of the three vectors should be equal to 0. Now, what are these three vectors? How do we find these three vectors? No, we could simplify this. This T1 could be extended into its standard basis notation form, or in its component form. You can utilize also that to solve for the T1 or the magnitude of T1 and T2. So if we could see here, the T1 has a component of X here towards to the left. So if this is towards the left, it is negative, no? And then upward, so since it is upward, then it is positive. So how do we solve for this? Now we have this triangle that represents this resultant, no? or the sum of this vector T1, we have this 50 degrees, and we have this component of T1, which is, let's say, T1x, and let's say this is T1y. Okay, so this vector T1 as a component of this T1x and T1y. So to find the component in x, we can utilize the cosine function. So the relationship of these two is cosine. So cosine theta is equal to adjacent over the hypotenuse. Okay, similar with the sine function, we have sine theta, which is equal to the opposite over the hypotenuse. Alright, so remember this. So therefore, our T1 and T1x can be represented as cosine 50 degrees. That is equal to T1x, no? Which we do not know yet, T1x over T1, no? So this magnitudes. So therefore, we could say here that the component here for the notation of T1 will be T1 cosine 50. Okay, later we will discuss this. And then for sine 50 degrees, we have T1y over T1. Yan. So if we simplify this, we cross multiply, the answer here will be for x, no? So for the x component, we have T1x cosine 50, sorry, not T1x, but T1 only, cosine 50, and then plus, sorry, with I hat, plus T1 sine 50 degrees j hat. Now, if you would recall, no, we have a directionality in our vectors. So if it is towards the left, it should be negative. So our x component, so the x component here should be negative. Okay, and then for the T2, so for T2, that will be the same thing. So for T2, we have this triangle to represent our component. Sorry, it should be this. So we have T2 here, the component T2x and T2y. The angle here is 32 degrees. So for the components of T2, we have, no, so I'll just do this directly, guys, similar to what I did here. So we have here T2 cosine 32 degrees I hat for the component in x, and then we have T2 sine 32 degrees for the component in y. Okay, so we have a positive in the x-axis since it is heading towards the right, and then a positive in the y-axis since it is heading upwards. Okay, so we already complete for T1 and T2. How about for the W? So for the W, we do not have space, but we only have a y, no? So it is only translating in the y-axis, so it doesn't have a component in x. So we have 0 I hat, and then since this is heading towards the down, so this should be negative. So this should be negative 100 kilograms. So converting this into newtons, so since we are talking about tension, converting this into newtons, we have 100 kilograms multiplied by the constant, no? So we have unit force that is equal to ma, and when you're talking about the weight, we have mg. So we have the gravity or the acceleration due to gravity, which is 9.3. Okay, j hat, got the j hat, and then equals to 0. So adding this to these vectors, simplifying this, and then equating to 0, we could probably solve for T1 and T2. Okay, so adding the x variables here, or sorry, the x components here, we have negative T1 cosine 50 plus T2 cosine 32, right, for the I hat, and then we have T1 sine 50 degrees plus T2 sine 32 degrees, and then plus, no, sorry, it should be negative here, so minus 100 times 9.8, this will be 980, right? 980, and then j hat, and then equals to 0. So now how do we solve this? So since we are equating to the 0, meaning the sum of this, or this this T1, negative T1 cosine 50 plus T2 cosine 32, this should be equal to 0 kasi nga, no, effectively, yung right-hand side natin ay 0. So, this should be effectively 0. No? So, the right-hand side is I or 0I hat plus 0J hat. Yung itong part na to. So, negative T1 cosine 50 plus T2 cosine 32, that is equal to 0. Therefore, we can find the relationship of T1 and T2. Let's just point out, we can solve for T1 first. So, I will just write this in T2, in terms of T2. So, lipat natin tong negative T1. So, we have T2 cosine 32 is equal to T1 cosine 50. So, we have this cosine 32 here. But if we cross multiply this will be dividing by cosine 32. Okay, so we have this first equation that we can utilize for solving T1 or T2. Okay, so for another equation, we could also equate this one to 0 then. You know, so what we did here, we could equate, again, we equated this to 0 to the right-hand side, and then also this one for J. So we have T1 sine 50 degrees plus T2 cosine, sorry, not cosine, but sine 32 degrees, and then minus sine 80, and then equals to 0. So again, we can form another relationship. We could try solving for T2 here. So T2 sine 32 is equal to, so we could translate this to the other side, and also this one. So we have 980 minus T1 sine 50, dividing this both sides by sine 32. So T2 is equal to 980 minus T1 sine 50 over sine 32. Okay, so how do we now solve this? So we have another equation here for T2. So we could solve this problem by equating this 2. So we could equate this T2. So this T2 is also equal to this T2. So T2 is equal to T2. That will be equal to, so we have this T1 cosine 50 over cosine 32. So T1 cosine 50 over cosine 32. And then equals to, we have 980 minus T1 sine 50 over sine 32. So solving for T1, okay, so how do we solve for T1 here? We can cross multiply this on the other side. And also for the other side, no, we can actually multiply this here. So let's try this now. So we have T1 cosine 50 degrees sine 32, and then equals to 980. 980 cosine 32 minus T1 sine 50 cosine 32. So we just distributed this by cross multiplication. So we want to solve for T1. So translate this to the other side. We have T1 cosine 50 sine 32. And then plus, we have T1 sine 50 cosine 32 is equal to 980 cosine 32. Okay, so dividing this both sides by T1. So T1, sorry, factoring T1 pala first, no? And then dividing this by this, or sige, factor na lang muna natin. So cosine 50 sine 32 sine 50 cosine 32 is equal to, we have 980 cosine 32. Okay, and then therefore dividing this both sides by this, no? So we have cosine 50 degrees 32, sorry, sine 32 plus sine 50 cosine 32. Okay, so therefore T1 is equal to, we have 980 cosine 32 over cosine 50 sine 32 plus sine, so hindi pa na tayo abot, no? Sine 50 degrees multiplied by cosine 32. Yeah, so therefore T1, that will be equal to, so let's use a calculator here, that will be equal to, what do you have here? 980. So 980 cosine 32 over cosine 50. Be careful with your calculator, baka naka-radian, no? So change this to degrees if the angles are in degrees. And sine 50 and then cosine 32. Okay, so the answer should be 839.25. So T1 is equal to 839.25. So what should be the unit? So again, force is equal to mass of gravity. That is equal to newtons, no? Or if you have here a conversion factor over K, effectively, usually we have, if this is in kilograms multiplied by meter per second squared, so this will be equal to newtons. So this, the unit should be in newtons. So this is actually the magnitude, no? Magnitude of your tension 1. So we want to find also the tension 2. So for tension 2, we have the equation. Either you utilize this or the other one or this one. No? So you can substitute T1 here or the other equation. So to make things easier, I'll just utilize this one. So this is much shorter. So we have T1 cosine 50 over sine 32, right? Sorry, cosine 32. Cosine 32. So the answer should be, so we have already an answer, so ans, and then cosine 50, and then over cosine 32. And so the answer should be 636.12. So T2 is 636.12 Newton. So now, what is this? This is also the magnitude. So how do we find the vector? No? So to find the vector, let's say we want to find the vector T1, okay, we could actually utilize what we utilized here. So we can just solve this again. We just want to substitute this T1. So the answer here is negative T1 cosine 50 I hat, and then plus T1 sine 50 degrees J hat. So we already know the T1, which is negative 839.25. Okay, so we can just solve this one. Sorry, 839.25 sine 50 degrees J hat. So the vector T1, that will be equal to, okay, we're gonna have to use it. We have to use our calculator. Okay, so we have negative 839.25 cosine 50. So we have negative 539.46 Newton I had. And then we have also 839. So I think we can just change this into sign. So the answer should be 642 plus 642 Newton J hat. Or sorry, meron pa palang point na. So 0.90. And then for T2, we have the unit is, so we have 636.12. So again, we have this for T2. So we have T2 cosine 32 I hat plus T2 sine 32 J hat. Yeah. So this will be equal to 636.12 cosine 32 plus 636.12 sine 32 J hat. So T2, that will be equal to, okay, so we have 636.12 cosine 32. So that will be 539.46 Newton I hat. And then for the other one, we have 636 sine 32. So let's change this up. Sine. Ayan. So So 337.09. So plus 337.09 J hat. Sorry, newtons, no? You have to include the newtons and the G hat. So these are your vectors representing your tensions. Okay, so thank you guys and see you in class.